Do you have any questions before we start? Anything? I mean, graph theory involves some proofs, like some arguments that a little bit more advanced than what we did before. So if you're not following them, if you're not understanding them, you should stop me and ask questions. Okay? That's the only way to learn anything. If you're here for 2 hours, don't waste that 2 hours, Try to understand by asking questions. Okay? Stop me and ask questions if you can't follow. I will also try to solve some questions today so that we know what kind of questions you'll be supposed to solve during midterms and final. Okay. Now we will be a little bit moving away from the Grimaldi book. We will discuss trees for a while, and now we'll come back to Euler circuits again, which is the next topic in Grimaldi. So for a couple of for this maybe 3 hours or so, we'll be discussing trees. So trees are a special form of graphs. You've probably seen it drawn on the board many times by many other instructors. There's a theory for trees, like they're special graphs, so certain things you can say. So what's a tree? A tree is a connected graph. So it's important that it's connected. Without any cycles. So cycles, remember, are the things that you start from a vertex, you move on edges, and you come back to the same vertex. So that's called a cycle. And for a tree, this is what we're defining. You're not allowed to have any cycles. Now, because it's also connected, trees look like this. Okay. So what is not a tree? For example, this wouldn't be a tree because you have a cycle here. Okay. It could also come out more complicatedly, but this is a cycle. So this is not a tree, and this is a tree. You can draw many other trees. Sometimes actually people draw trees in a sort of graded way, sort of with some centers. But we don't necessarily write the tree in a graded way. So it could be drawn like this, doesn't matter. Like we don't really think that there are layers. Those are usually called Hasse diagrams and so on. I mean, we don't want necessarily a shape like this. It could be like this. What is not a tree also is, suppose you have this tree and this one next to it. So if you have such a thing, this is not a tree because it's not connected. Now, we will be facing these kind of situations where you have graphs whose each connected component is a tree. They will be called forest. Okay? So a graph is called forest. It's called forest. You can see the language is very much like trees and forests. So you could have a forest means lots of trees. Called a forest if each of its connected component is a tree. Each of the connected components is a tree, makes it a forest. So forest is basically you have a bunch of trees, and associate the forest, you always have number of trees in it, number of components. And this number of components here, for example, is 3, will be related to number of edges and number of vertices. Okay. So if you look at this tree, for example, you have you have 6 vertices. Okay, so this has 6 vertices, and if you look at its edges, you have exactly 5 edges. So it turns out that any tree you draw, it will be always the case that you have exactly 1 less edges. Okay? So in a tree, you will always have, if you have n vertices, n minus 1 edges. Okay? So this is actually our first observation about trees. So this is a theorem. A graph with n vertices. We will also claim the converse is somehow true. Is a tree, so a graph is 3. If and only if it has n minus 1 edges, so 1 less edges, and no cycles. So a tree has no cycles, which makes sense. But the statement also says that they will always have n minus 1 edges. So for a forest, this is a forest. This is disjoint union of all the trees in it. So this is the first tree, second tree, third tree. So for a forest, this theorem will tell us that number of edges on a forest minus number of vertices minus number of edges will be exactly the number of connected components. So this is the conclusion. This is the conclusion. If G is a forest, say vertices and edges, then if you look at the number of vertices and subtract number of edges, which you can do it here, you have V1, V2, V3, V4, V5, V6, V7, V8, 9, V10, 12. So number of vertices is 12. If you look at the edges, number of edges is 9, and the difference is the exact number of components. So this will give you the number of components. Okay. So you can see, whenever you have a forest, which means it's a graph with no cycles, whenever you have a graph with no cycles, you can say that its vertices minus number of edges counts the number of components, which is a very nice, effective way of dealing with things. So it comes from this, of course, because on each component, the difference is 1. So if you have 3 components, difference becomes 3. Okay? It's a very easy thing to see why the conclusion is true once you assume that this is true. Okay? Because on each component, difference is 1. If you have 3 components, difference becomes 3. So why this is true? Now, for this, we have to argue with there are a couple of different ways to prove it, but if and only if means both ways are true. So we'll take this way first. Suppose that we have a tree. So a tree looks like, some vertices, some edges, and no cycles. Okay? So you're not allowed to have cycles. So you cannot have things like this. But you have vertices. And some edges, randomly written. Okay. So the argument is that given a graph like this, which is a tree, anytime you choose an edge and erase that edge, anytime you erase an edge, the graph becomes disconnected. Anytime you take an edge out, the graph becomes disconnected. So every edge is a sort of, they're called bridges. An edge is called a bridge if when you took it out, your graph becomes disconnected. Okay? So on a tree, every edge is a bridge. First claim is this. Why is this true? Take one edge out. That edge connects two vertices, right? Now, suppose that when you take that edge out, you don't get disconnected. That will mean that these two vertices are connected by something else, by a cycle, by something like this, right? So if you still have connected graph once you take this edge out, that means with that edge you have a cycle. Okay? Otherwise you wouldn't be connected when you take an edge out. Okay? On a tree, every edge is a cycle. Every edge is a bridge, meaning that once we take it out, we get a disconnected graph. The reason is that tree has no cycles, okay? If this was not the case, say an edge, we say an edge E from V to W is not a bridge. Then V and W should be connected, should communicate in the graph where you take out the edge E. So when you take the edge E, they should still communicate. But if they communicate when you take this bridge out, that means then with E, we will have a cycle. But it's a tree, so no cycles are allowed. But G is a tree, so no cycles are allowed. It has no cycles. Because it has no cycles, that means this cannot happen. That means this cannot happen. That means it's a bridge. Okay? So what does we just learned? On a tree, if you take an edge out, you get two components. Okay? Repeating this process, okay. Suppose inductively we take, suppose one by one, we take we take k edges. So when you take one edge, you get two components. But when you choose a second edge, so we took this edge out, we got two components. But then you take a second edge, you choose another edge, you take it out. When you take that edge out, you again get two components out of that component, which means totally you will get three components. Right? And then if you do this again, you get four components. So if you take k edges out, the resulting graph will have how many components? If you take one edge out, two components, k plus one components. So we get k plus one components if you take k edges out. Okay? Now, suppose you take out n minus one of them. The resulting graph will have n components and n vertices. If you have n components and n vertices, what kind of graph you can have? Huh?
No edges.
It's what?
No edges.
No?
No edges.
No edges. Yeah, it can only be a graph with no edges. Okay. Such a graph can have no edges. Such a graph has no edges. That means if I take n minus 1 out, I finish all the edges. And that means I actually have to check. We have at least n minus 1, but I guess that's more clear. I mean, you can never be, you can never have more components than number of vertices, okay? So you cannot really have more than n minus. So this means do I have to check the original one? I mean, this only means this, but you can also see that if you have less than this, then your graph cannot be connected because you'll be reaching to, you run out of edges too fast, basically. Right? Original thing is no components. You get to k plus 1 components and no edges left, which you should have n components. So this actually means it's equal. I don't know if you can follow this. I mean, both sides are actually follows from this argument. So I suppose you have very few edges. Once you take those edges, say k of them, much less than n minus 1, then you will be, after k edges, you will have k plus 1 components, but you will have discrete, no edges left, right? So if you have no edges left, and you still have n components, like, let's try this. So we want to obtain the number of edges n minus 1. So that number of edges is some number e, okay, or L. If we take, if L is, say, less than if we take L edges, so suppose L is much less than n. I mean, this only tells you that L should be at least n minus 1, but the other direction is also clear. If it is much less, then if you take the L edges out, say you only have like 3 edges or something. If you take those out, you get this many components. So it's much less than n, and no edges. But then you only have n vertices and no edges. We must have n components. So we again get the problem. Okay? So we say this many components, but this many is much less than n. But we should have n components. So this is again a problem. This is again a contradiction. So you cannot really have much less either. Okay, you cannot have less than n minus 2. This argument shows you cannot have too many either, because then you will be running out of edges too fast. Other alternatives to this, you could do an induction. You could take an edge out, and on each subgraph you could assume that this theorem is true.
In this part, this means e smaller or equal than n minus 1.
Yeah, I guess. Because that argument proved that it's bigger, right? Yeah. Thank you. Mm-hmm. So this argument proves that it's bigger. And then this argument proves it's smaller. This whole discussion actually covers other case too. So if G has n minus 1 edges and no cycles, so when you have no cycles, you again can say all edges are bridges, right? Then by repeating the same argument, we can show that say original G has, say, C components. Then when you take n minus 1 edges, you should have no components left. So number of components of G minus number of these edges, n minus 1, should be only the vertices. So this has n components. So from this, you get the number of G. So anytime you take an edge out, you add 1 to the number of components. So when you have n minus 1 edges, you take them one by one. And then at the end, when you take all the edges out, this will be the number of components. But you'll have no edges left. If you have no edges left, you should have n components, which means you should have the equality, and that proves number of components at the beginning is equal to 1. Okay. At the beginning is 1. But for a graph which has no cycles, to show that it's a tree, you only need that it's connected. So G is a tree. So we already know that it has no cycles. Trying to show that it's a tree, we show that it has only one component. Okay. We could have used this probably much effectively, but this is how it goes. Let me write one more thing. Okay, so let G be a graph. For each vertex V in the vertex set, the degree of the vertex, the degree of V is defined as, so degree of a vertex is the number of all the vertices that are connected to V by an edge. Okay? So this is number of all the vertices such that EV is an edge. Okay, so it's the number of vertices attached to a vertex. So it could be a complicated graph, such thing. So all you care about is how many edges are attached to a vertex. So here, for example, for this vertex, you look at 1, 2, 3, 4, 5, 6. So for that it's 6. For this vertex, there are only 2. For this W also 2. Let's make it 3. So for W, it's 3. For this one, say call the Z, for that vertex, it's 1. So degree is the number of vertices that are attached, or number of edges coming out of your vertex. You could also see it in the picture like that. Now, while we discuss degree will be crucial to understand trees as well. So for trees, we'll look at the degrees and we'll try to see it. For degrees, the most basic observation is this. If you take a graph, say this one, one, two, three, four. If you look at the degrees, The basic observation is that the sum of degrees is something that related to the graph. Can you see what it is? So if I sum all the degrees, you get 8. Is 8 something? Maybe I should throw some more edges. Anyway, I don't know. Let's throw one more. So it's 10. Is this 10 anything from the graph you can read of? Huh? Yeah, it's twice as much as the edges. And the reason is very obvious, because when you calculate the degree, you're calculating an edge. First is the degree of this vertex, and then again as a degree of this vertex. So every edge is counted twice in the sum. So you can say that the sum of the number of all the degrees over all the vertices is always twice as the number of edges. Okay. In particular, for a tree, we have, so on a tree, when you sum the vertices, you get 2 times n minus 1 on a tree with n vertices. You get the number of degrees. The sum of the degrees is twice the n minus 1. Using this, we want to prove 2 statements. Normally, it's kind of, so one of the statements is this. Every tree has at least 2 vertices with degree 1. So it turns out degree equal to 1, such a vertex is called a leaf. So basically it says every tree has at least 2 leaves. And you could have more than 1, more than 2 in some cases. This one has 1, 2, 3, 4. But you could also see that in worst cases like this one, you can only have 2 leaves. So 2 is absolute minimum, of course. You cannot draw a tree with only 1 leaf, because, or no leaves. For example, if you draw a tree like this, where everything has degree 2, you have a cycle. So it cannot be a tree. So if you want to avoid the tree, if you want to avoid having a cycle, you have to have at least 2 leaves. Basically, that's the idea. And you could have more. You can have more. This is still a tree, but you have 1 more leaf. So you can have more leaves, of course, than 2. But is there any way to show this with some inequalities, some numbers, maybe using degrees? So it turns out that you can show that you have more than 2 leaves using this inequality. So this is the idea. This is the argument, proof of the proposition. Suppose that the tree, T is a tree with one or no leaves. You have either one or no leaves. So a tree has vertices and edges. So aside from 1, maybe, all the other vertices have degree 2. Okay? Aside from 1, maybe, aside from maybe 1, one vertex, all the vertices have degree bigger or equal to 2. So maybe one of them have degree 1, but suppose all others have degree 2 or bigger. Then you could add these things. So when you add all the vertices, what do you expect to get? All of them, except maybe 1, have more than 2. So that one you can add, but you still will have something bigger than 2 times n minus 1 plus 1. Right? Right? There's no. So what do you expect to get? So all of them, except maybe 1, has degree 2. So that means you get 2 times n minus 1 from them. And with the last one, maybe 1 more. But you can be absolutely small as you get this. You cannot get anything smaller. Okay? But at the same time, this is 2 times number of edges. But we already showed the number of edges is always n minus 1. So this total is 2n minus 1. So you get 2 times n minus 1 here, 2 times n minus 1 plus 1 here, but this is absolutely smaller, like smaller equal to. That means it's not possible. Okay, this is a contradiction. This is a contradiction. So you cannot have a tree with 1 or 2 leaves. You should have at least 2 leaves. Now, some of these were abstract math, like, now I want to do an explicit calculation with you, if you can bear with me. We'll prove or do a counting of number of trees on a vertex set. So this is a theorem. It's usually called Cayley's theorem. There are n power n minus 2 different trees on a vertex set. Size it. Now this is a counting problem. There will be no proofs, like there will be no abstract thinking. We just need to use oral counting abilities, all our full force, whatever we learn in this course. Actually, we'll be using everything we so far learned in this course, including all the things I proved. So these things look like a little bit abstract, but they will be used in this. This is something that you may want to know because, say you're dealing with 3 vertices, 1, 2, 3, you may want to know how many possible trees you have. So how many possible ways of making a connected graph without too many edges. See, trees are good because trees are efficient. We'll see later that if you want to find a connected subgraph of your graph in the most efficient way, that means you should not have cycles. Because anytime you have cycles, you're wasting money. People can be connected 2 different ways. You don't need that. So if you're given a graph, if you want to solve questions like, what's the minimum spanning tree? Like, what is the minimum subgraph that this is still connected? You sort of choose this, but not this one. Because you don't need this extra edge. And then what you end up with choosing is a tree. So you can, if you want to minimize your cost to get still a connected subgraph, you should choose a tree. Because cycles are a waste of money. Because of that, trees are important for finding minimum spanning subgraphs. They will be always trees. Now you may want to say, I have 3 restaurants. I want to put some edges between them, some communication lines. How many different ways I can do this? Suppose you have 1 million restaurants, and how many ways I can still keep them connected? So this is the question we're asking here. How many possible trees you can form for number of n edges? And the answer, this theorem says, is this number. Okay, so it's a nice theorem. It's a good thing, but we have to use counting abilities to see this. So we'll be looking at all the cases and so on, and then maybe get an idea how to do it. So for n is 3, this is one of the spanning subtrees. This is a tree because it's connected. This won't be a tree because this is not connected. This is a tree. You could also use this. You could also use this. So you actually have three different trees, 3 possible trees. And this is exactly what this says. It should be, say, 3 minus 2. So 3. That's correct. N equals 4. You expect that it should be 4 to the 2. So you expect 16 different trees. I can draw some of them, but so with 4, this is a connected graph, which has no cycle. So this is a tree, for example. You can sort of say, okay, I want to do this in different ways. You can say these are all. But then I can say, how about this one? This is still a 3. And you can move this. I have 8. I only got half of it. So what else it can be? Huh? Z, huh? So you could have Z's. You could have N's. I don't know. You could have same thing. This one. No, this one, I guess. 4 tane de böyle çıktı. So we want to make sure they're all different too, right? So I need 4 more. What else could be?
You can have cross over line.
Nasıl? Buradan sağ cross
And then line combining top.
like this. That's possible. Yeah. So you could have line cross, line cross, line cross. So we get 4 more. So we got all 16 pro. For n equals 5, we expect 125. Sorry, no. So it's hopeless to be able to write all of it down, right? It's a big thing. So our only hope is to be able to understand it, maybe some way inductively, how to get the next ones using a smaller shape. Do you remember the movie Good Will Hunting? Anybody watched that movie? Good Will Hunting? The story is that there's this janitor who cleans the building in MIT, and then he walks in the corridors. One day he sees this question on the board, and then he goes and draws all the possible 10 different graphs they were asking, and then the professor looks for him and so on. He makes him he makes him start working there. So some of these questions that you see, sometimes it's just brute force, some intelligence. You can just come up with why it's true. So we'll have 10-minute break. Maybe on the break you could come up with some argument. But we will be able to write everything and see that after the break.